Okay, so today we're looking at experiment 16, which is the Grignard reaction of a ketone, in this case benzophenone, in order to generate triphenylmethanol. So in this case, the first step to generate our Grignard reagent, which will be phenyl magnesium bromide, we're going to weigh out approximately 19 milligrams of polished magnesium fragments. So please record the mass of magnesium utilized in this reaction, and we're going to then activate the magnesium with iodine, and then we will add our alkyl halide, which in this case is bromobenzene, to generate phenyl magnesium bromide. Okay, so I did this next step pretty quickly because we want to make sure that our reaction setup remains as dry as possible. So to my conical vial, I've added the magnesium previously weighed, a crystal of iodine, and 100 microliters of diethyl ether as before. I've set up my hot plate to begin heating my sample, and will ideally reach a bath temperature of 40 degrees Celsius as noted on our thermometer. So now, as we notice, this entire setup has been oven dried and allowed to cool in a desiccator. We already have our drying tube prepared of calcium chloride, and all components of our setup are linked with O-rings on each seal. We also have the septum up the top for the addition of our reagents. What we're now going to do is we're going to place our conical vial into the heating jacket, into our heating bath, and we're going to allow our sample to heat until we begin to observe the characteristic presence of the iodine vapor. Now, this is going to take a little bit of time, and it may be a little bit hard to see on the camera. That's why we provided the supplemental recording. One thing that I would like you to note is that if you, let me just make this a little more. There we go. Okay. So we're going to allow this to heat to approximately 40 degrees Celsius until we observe the characteristic purple iodine vapor. We're activating our magnesium to further facilitate efficient formation of our Grignard reagent. And noting from our thermometer here, our bath temperature is approaching 40 degrees Celsius as required. So we'll allow this mixture of magnesium and an iodine crystal to heat for approximately 3 to 5 minutes, and once we observe the characteristic purple iodine vapor, we'll raise our sample up from the heating mantle and we'll begin initiation. Okay, so we've allowed our sample to stir and we've observed the characteristic iodine vapor. We've also noticed a slight color change in our magnesium iodine mixture. So we're now ready to proceed to the next step. So as part of the next step in our procedure, we're going to keep our bath at 40 and we're going to cut the external heating and just let the heat of the bath maintain our temperature. We don't want to have supplemental heating along with this initiation temperature, as initiation is exothermic and we really want to make sure that it's not going to run away from us. If it gets too hot, then you'll end up boiling off the ether, potentially generating side products, and overall reducing your isolated yield of pure product. Okay, so as such, our first order of business is to add 100 microliters of diethyl ether into our reaction mixture. So here is the diethyl ether. Here is our syringe that we're going to be using, and we're going to add the diethyl ether. Okay, we've added our diethyl ether. Now for the actual reaction itself. So here we have 76 microliters. We have 76 microliters of bromobenzene in 400 microliters of diethyl ether. And the reason why this solution is relatively dilute is we want a slow dropwise addition to minimize exotherms. So we're going to add this mixture dropwise through our septum using our syringe. So for the first initiation step, we're going to add, let me zoom in to the top portion. We're going to add 6 to 8 drops of this solution dropwise. This is to facilitate initiation. If initiation has not occurred, if we don't see the bubbles on the surface of our magnesium, then you need to wait, because if you add all of your reactant at once, you're going to end up with initiation occurring, generating an exotherm, and then subsequent reaction generating additional heat. We're going to save this vial that we drew from. Going to save our vial because we're going to rinse it through with another aliquot of diethyl ether. For now, let's begin our addition. So we're going to add 6 to 8 drops. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and now what we're going to do is we're going to wait for a little bit, and we're just going to allow this to stir. And I'm taking a look, and I see bubbles forming on the magnesium. So now what I'm going to do is, as I'm seeing that characteristic reaction on the surface of our polished magnesium, I'm now going to add the remaining contents of our syringe, dropwise over 3 to 5 minutes. Slow addition, watching for reflux. So again, we're continuing our dropwise addition of our bromobenzene solution. We've already initiated Grignard formation, so now we're completing the dropwise addition of our alkyl halide, making sure to watch and ensure that it's a gentle reflux at most. You ideally don't want to see it refluxing, but this reaction just does generate a fair amount of heat, even at a small scale. So we've completed the addition of our first aliquot. Now what we're going to do is we are going to rinse the contents of our vial with an aliquot of ether. So here's our empty vial that we drew our bromobenzene from, and we're going to rinse it with an aliquot of ether. So we have added an additional We have added an additional 300 microliters of diethyl ether, and now what we're going to do is we're going to add this rinse aliquot in one portion. This just ensures all of the bromobenzene that we added to our vial and it ends up directly transferred into our reaction mixture. And it also ensures that we have a reasonable amount of solvent. Okay, so we're going to add this aliquot via fast dropwise addition. Okay, perfect. So now that we have added all of our reagents, now that we've added all of the initial set of reagents, we're going to allow this mixture to stir at 40 degrees Celsius bath temperature for 15 minutes. In the meantime, we're going to prep the other reagents that we're going to be utilizing in this experiment, and we're going to be preparing our solution of our second reactant, which is benzophenones. So, as part of the preparation of the benzophenones solution, we have weighed out a defined amount of benzophenone, and then we're going to dissolve it in 300 microliters of diethyl ether. So please record the mass of benzophenone utilized at this time. So here we have our acetophenone successfully transferred to our clean and dry vial. We're then going to dissolve it in 300 microliters of diethyl ether. Just as a correction, it's the 105 milligrams of benzophenone dissolved in 300 microliters of diethyl ether. So we're still waiting for our preparation of the phenyl magnesium bromide. It's almost time, and once the 15 minutes of heating has passed, we're going to allow our mixture to cool to room temperature. As 15 minutes have passed, we're going to cut the heat, and we're going to allow our Grignard reagent to cool to room temperature. So let's raise it up out of the bath. Okay, perfect. So as you notice, the reaction mixture's color has changed substantially, and this is a reasonable sign that we have generated our Grignard reagent. So we're going to allow this mixture to cool, and then we'll continue on with the addition of our ketone reactant benzophenone. Okay, so we're going to continue on with this procedure. Our mixture is now cooled to room temperature, and so we are going to add the benzophenone solution dropwise through the top of the septa. using our syringe. We're using a fresh syringe for this. And we're going to add this mixture quickly, dropwise, over a 30-second to 1-minute period with reasonably vigorous stirring. You just want to make sure that it's at most maintaining a gentle reflux. Okay, so we've completed our first addition, and now what we're going to do is we're going to rinse our initial flask, our initial vial, with an additional aliquot of diethyl ether. We're then going to add the rinse aliquot in one portion quickly. Okay, we're going to allow this reaction mixture to stir for 1 to 2 minutes, and then we're going to allow the mixture to cool to room temperature. As you may notice already, the reaction mixture is beginning to solidify. So we'll allow this mixture to stir for another 1 to 2 minutes, and then we will unhook the mixture from the claisen head setup. Okay, so as the required 1 to 2 minutes have passed, we're going to carefully unhook the claisen setup. Then we are going to cap our vial. And we're going to allow the mixture to continue to stir. And during this time, we're going to see, as we are already beginning to see, solid crashing out from our solution. Do you see how the solution is becoming more and more heterogeneous with stirring? That is the sign that our product is beginning to precipitate out of the solution as the mixture cools and any heat generated from the exothermic reaction begins to dissipate. So we'll allow this mixture to stir for a few minutes, and then we'll begin isolating our product via hydrolysis. Okay, so we're going to begin the process of neutralizing our mixture and isolating our desired product. So To do that, we're going to treat this mixture with 3 molar hydrochloric acid, and we're going to be breaking up the residue using a stirring rod. Okay, so we have our hydrochloric acid all set and ready to go. We're going to uncap our vial. We have our stirring rod also prepared. And we have a piece of litmus paper that we're going to use to test to make sure the solution has been properly acidified. Okay, so now what we're going to do is we are going to add our hydrochloric acid until the aqueous phase, which is going to be on the bottom. Tests litmus red has been acidified, and we should see a clear division between the organic ether layer and our aqueous layer. It's important that you add the hydrochloric acid dropwise, because as you notice, it is bubbling quite vigorously. If you add it too quickly, you're going to get a runaway exotherm. And in turn, your mixture will splatter. It's important to be patient and utilize efficient stirring. Now, there's no need to start testing it right now because likely we're not going to see it properly acidified. Once we start to see a clear separation of the organic and aqueous layer, that's a sign that we should start to test. So now I'm going to start to use the stirring rod, and you have to be careful because when you start to mix, you can end up initiating a reaction. So I'm going to turn off the stir. And as you notice, we're starting to see a clear division between the organic and aqueous layer. I'm going to go to the bottom, and then I'm going to try to test the aqueous layer on my litmus paper with just a drop. Okay. So I'm going to save this rinse because it's important that we don't lose material in this step. So as you can notice, our pH paper, when we put a spot on, it's testing litmus red very clearly. Litmus red. Does everyone see the 2 red spots? Okay, perfect. We also have noticed we went from a heterogeneous solution to a quite homogeneous solution. So now what we're going to do is we're going to carefully separate our aqueous and organic layers, and we're going to transfer the organic layer. We're going to transfer our organic layer, in this case, into a conical vial. Okay, so we're going to remove our aqueous layer and transfer it into a clean and dry conical vial, and then the organic layer will be utilized, but not quite yet. Okay, so now we're going to transfer our aqueous layer carefully into, let's change up the, okay, perfect. So we're going to transfer the aqueous layer into a conical vial. Now what we're going to do is we're going to take this aqueous layer and we are going to sequentially extract and treat our aqueous layer with 0.5 milliliter portions of diethyl ether. So let's add our first portion. Okay, so we've added the first portion, 0.5 milliliters of diethyl ether. We're now going to cap this mixture and we're going to agitate and mix the aqueous and organic layers, which are currently separated. Remember, since we're dealing with diethyl ether is less dense than water, so the diethyl ether layer is on top while our aqueous layer is on the bottom. Important not to get them mixed up. Okay, so we're going to take our vial over to the vortex mixer and we'll resume once we've completed this first agitation step. Okay, so as you can clearly notice, as you can clearly see, the top layer now has the characteristic color associated with our organic layer and our product mixture. That's a very good sign, as that indicates that we likely have extracted some of the colored organic material into our organic phase. So now what we're going to do is we're going to carefully transfer our upper organic layer into an Erlenmeyer flask. Okay, we're now going to repeat this extraction process with another aliquot. I'm going to repeat this extraction process with another aliquot of diethyl ether. We're then going to subject this mixture to vortex mixing again, and we'll resume once we've completed vortex mixing. So we've finished mixing our organic and aqueous layers, and again, just like before, we're going to decant the upper organic layer. We're then going to do a third and final extraction of our aqueous layer. We're then going to mix the organic and aqueous layers, and then from there we'll remove our organic layer once again. So we'll resume after mixing for our third and final time. Okay, so now that we have finished mixing, we're going to remove our organic layer once again. Okay, so we're going to save this aqueous layer for later. Never throw anything out until you're done with an experiment. If material is lost in the aqueous layer, you want to be able to go back and extract it without having to redo the entire experiment. Okay, so now what we're going to do is we're going to take these rinses and we're going to combine it with our original sample. Next, what we're going to do is we're going to take this mixture and we're going to rinse it with 0.5 milliliters of chilled deionized water. This is just to remove any acidic residue. Okay, perfect. Now we're going to subject this mixture to vortex mixing, and we'll resume once we've completed that step. So we've finished mixing, and now we're going to combine and transfer all of our organic layer components into an Erlenmeyer flask in preparation for drying. Okay, so as discussed, we're going to transfer our organic extracts into an Erlenmeyer flask in preparation for drying and then evaporation. What we're then going to do is we're going to transfer the aqueous layer into a separate container. So we have our organic layer. Now let's transfer the aqueous rinse into our aqueous container. Just so that way if something's lost in the aqueous phase, we can go back. Okay, and we'll resume when we discuss the drying step. Okay, so I've taken the liberty of rinsing some of the product residue that was on the top of the reaction vial into our combined organic layer mixture. Now what we're going to do is we're going to very carefully add sodium sulfate, approximately 300 milligrams, to dry our reaction mixture. Now we should zoom in here as it's really important to note a few things. So we want to add enough sodium sulfate so the sodium sulfate is free flowing. If it's clumping at the bottom, that's a sign that likely the solution has a lot of water and we need to add a little bit more sodium sulfate. So we're going to add some more sodium sulfate and we'll resume once we've finished drying and mixing our sodium sulfate with our ether layer. Okay, so as part of determining the isolated crude mass of product, we weigh out a Craig tube in a pre-tared beaker, and the Craig tube has a boiling stone in it. So please record the mass of the Craig tube and boiling stone, which you'll need to calculate the crude yield. Okay, so we have our dried mixture. We made sure that the ether layer is completely clear. You may have to add a fair amount of sodium sulfate to get rid of all the water, and you want to make sure the sodium sulfate is relatively free flowing. And we also have our Craig tube. And what we're going to do is we're going to transfer 0.5 milliliter portions of sample into our Craig tube, and then we're going to evaporate our diethyl ether using a sand bath set to 40 degrees Celsius. So we'll begin this transfer process and then allow our sample to evaporate. Okay, we're going to place the sample in our sand bath. And we're going to allow the mixture to evaporate and our diethyl ether solvent to evaporate. And then once it has completely evaporated, we'll add another 0.5 milliliter aliquot and repeat this process. In the meantime, while our solvent is evaporating, I've prepared a thin layer chromatography plate, or TLC plate. So as you notice, the TLC plate is designed in the presence of a solvent system to help resolve and separate components of a mixture, and it's used to help us get a sense of how many components are in our mixture and the relative difference in RF value. If we wanted to run a column, for example, spotting your sample and running a TLC plate in your column solvent system is a wonderful way to get a sense of the separation between your two components. So what we're going to do is we're going to very carefully spot from our crude reaction mixture. And we're going to carefully spot our crude reaction mixture, and then we're going to carefully put as small of a possible dot on each of our designated spotting areas. Okay. Now we're going to allow the deposited solvent to dry, and then we're going to transfer this TLC plate into our development chamber. So here is the development chamber that contains our mobile phase solvent, which is dichloromethane. Based on the interactions between the mixture components that we've spotted on our plate, the stationary phase, which is our silica gel, and the mobile phase, which is dichloromethane, the mixture components will move up the plate with different retention times or retention factors. And as a result, the two mixture components will be resolved on this TLC plate, as both the mixture components will move up the plate to a varying degree based on their molecular polarity, structure, interaction with the stationary phase, and interactions with the mobile phase. So what we're going to do now is we're going to load our TLC plate into the chamber. It's important that your spots do not end up below the solvent level. Okay, so a few things to note here. Notice how the solvent level is below our spots. And do you notice as the solvent begins to move up the plate, our mixture components begin to become resolved. Different mixture components will have different interactions with the mobile phase and stationary phase, and as a result, our mixture components will move up the plate in varying degrees. We're going to allow the solvent to elute all the way to within 2 to 3 centimeters from the top of our plate, and then we will note and visualize our spots via UV light. Once we have visualized our spots, we'll circle our spots and identify the mixture components. So we'll allow this sample to run up the plate, and we'll allow this TLC plate to fully run, and then we're continuing on, of course, with the evaporation of our diethyl ether, so we'll check back up on that. So as you can see, our diethyl ether is evaporating upon heating. We're going to continue to evaporate off the diethyl ether until we've obtained our crude solid residue. So our dichloromethane has almost completely eluted up the plate. So now let's remove our TLC plate. There we go. So let's remove our TLC plate. And now it's really important, let's put this back on. It's really important that when you remove your TLC plate, you note the last location of solvent. So notice how I made a mark in pencil. That mark is signifying the last indicated location where our solvent front was at. Now, as you can see already, there are faint visible spots where our compound is likely present, or one of our mixture components is likely present. So what we're going to do is we're going to visualize these spots using UV light. It's a bit hard for the camera to capture, so one moment. Okay, so after visualization using UV light, I was able to identify the following two visible spots. You can verify this as well. It's very hard to see on the camera, but in the presence of UV light, those two spots which correspond to components of our product mixture were clearly visible. So from this information, we'll compare our observations for our crude product mixture to the product mixture after purification. So after analysis via UV, here is our TLC plate. As you notice, we have a major and a minor spot. The minor spot is likely a byproduct that we will separate from our reaction mixture via purification. In this case, purification calls for trituration with ligroin, which is a nonpolar solvent that is especially useful for removing nonpolar and aromatic impurities such as biphenyl. You'll also see a picture of this TLC plate on canvas because you'll need to assign RF values to each of the mixture components and in turn match the experimental RF values to the literature RF values for biphenyl and triphenylmethanol. In preparation for subsequent separation of biphenyl and the triphenylmethanol, I'd like you to record the mass of this 10 milliliter Erlenmeyer flask that we are going to use to collect our biphenyl extraction residues, as well as finally concentrate and isolate the biphenyl product. So please record the mass of this 10 ml Erlenmeyer flask that we're going to use as part of our isolation of the biphenyl byproduct. Okay, so we finished the evaporation step, and now let's record the mass of our crude residue from our reaction in our Craig tube. Okay, so continuing on, we're going to purify our crude mixture via trituration with ligroin or painter's naphtha. We're going to use a small aliquot. Okay, so now that we've added the painter's naphtha, what we're going to do is we're going to triturate our mixture with our stirring rod. What we're doing essentially is we're attempting to break apart the solid and pull off any of the potentially soluble impurities. And ideally at the end, we'll just be left with a pure sample of our target material. So we're going to triturate, and we want to make sure that we're really thorough with the trituration, that we've captured as much of the solid as possible, and we've broken it up so that way we can get as much of the impurities separated. And we'll resume once we've completed this trituration for about 5 to 10 minutes. So again, in trituration, we're just breaking apart our solid to attempt to dissolve any of the soluble impurities. Okay, so we've loaded our sample and we've capped our Craig tube and placed it in a glass conical tube. And the goal of this process is, as we centrifuge this mixture, we'll separate out the supernatant liquid. We'll separate out the liquid that we use for trituration, which contains many of our impurities, and we'll be left with our slightly purified solid. So we're going to load this sample into our centrifuge and then centrifuge for approximately 1 to 2 minutes to further separate our liquid and solid. So we finished centrifuging our sample, and our solid and liquid should be separated. We're going to repeat this trituration process for a total of 2 times. So as you can see, after trituration, we have separated the liquid and solid components. Now we're going to repeat this trituration process 1 additional time. So now we're going to rapidly triturate the solid once again. And we'll resume once we completed this trituration process. Next, what we're going to do is we're going to transfer our rinses with Ligroin into a tared Erlenmeyer flask that we weighed previously. We're going to evaporate these rinses in order to estimate the amount of biphenyl coupling product observed. So we have our Craig tube prepared for centrifugation, and we're going to separate our solid and liquid components. So we're going to place this tube in the centrifuge, and in the end we'll have enriched the purity of our isolated crude product. So as you can see now, we've separated our solid and liquid components, and we now have a light brown solid. It's not perfect, and we can clean it up further via recrystallization, but this provides us a good entry point, and we'll check its purity via TLC and other spectroscopic techniques. Again, we're going to transfer the Ligroin rinses into an Erlenmeyer flask, which will then evaporate on a sand bath in order to estimate the mass of biphenyl coupling product. So now we have our triturated solid product, which has been purified via trituration. Notice how it's a lighter color brown now, as we've removed many of the colored impurities. If we wanted to clean this up further, we can recrystallize it. We're then going to place it in the oven for approximately 5 to 10 minutes and then record the dry mass of our purified product. We're also going to I've also taken a small sample of solid and dissolved it in diethyl ether in order to analyze this purified sample via thin layer chromatography. So we're going to analyze the purity. I've dissolved a little bit of our purified product in diethyl ether, and we're going to spot that. And we're going to look at the composition of our purified product and crude mixture via TLC. Now, what's new here is that I've added a co-spot. Now, this co-spot is utilized for direct comparison between the spots observed in two different mixtures. So I'm comparing my purified product mixture to the Ligroin rinses. So we spot 3 lanes: the crude rinses, the purified product, and a co-spot. And the goal of this process is that if we have identical compounds in the purified mixture and our crude product, the spots should line up. If there are different compounds, the spots would be different. And the co-spot serves as a verification, as it's a mixture of the 2 component lanes. Okay, we're then going to elute and run this TLC plate, and then we'll look at the final results once it's run up the plate. So after drying, we're now going to record the mass of our isolated product after trituration in our first purification attempts. We're then going to assess the purity by taking a proton and carbon NMR, as well as measuring an IR spectra and a melting point. So please record the mass of isolated product after trituration and purification. Okay, so we have our sample. I've already transferred about 2 milligrams of our solid sample into a pestle, mortar and pestle. And what we're going to do is we're going to mill and grind our solid. And you notice once we start to mill our solid, it adopts a much lighter color. And essentially we want a nice finely divided powder, or as finely divided as we can get it. And in this time we're not going to be using a KBR disc. We're going to be using Nujol, which is mineral oil. So we have our 2 salt discs set up, and now what we're going to do is we're going to take our Nujol, and we have our stirring rod, and it's important that we do not allow the stirring rod to touch our mixture, directly. So we're just going to let a drop fall. And then what we're going to do is we're going to mill our mixture with the nugel. And now we're aiming for a mixture that's not too opaque, but not too dilute either. Okay. So then once we have finished milling our mixture, we'll be able to transfer it into our salt plates for IR analysis. So after milling and mixing, we have our sample ready to go. And now what we're going to do is we're going to dip the pestle into the mixture and then gently add a drop into our salt plate, and we'll repeat that one more time. Okay. Now what we're going to do is we're going to press our sample between the salt plates gently. We don't have to grind it or anything, just a gentle press. So now we have our sample stuck between our two salt plates, and we're ready to load the sample onto the IR. So we finished collecting our IR spectra, and a copy of this spectra will be provided on Canvas. Overall, it looks reasonable. We see our characteristic aromatic peaks, as well as a tiny alcohol peak. We also happen to see something that's quite interesting, as it provides solid evidence that we've generated our desired product, as we have observed, and we see an sp3. We see some sp2, and we even see some sp3 signals. So you're responsible for working up this IR spectra and assigning the peaks and comparing this IR spectra to that of the known spectra of our product of triphenylmethanol. So for completeness, we've also decided to run an NMR of our sample. So we dissolved our sample in deuterated chloroform, and now we're going to collect a proton and carbon NMR. And the proton and carbon NMR will be posted on Canvas. So for completeness sake, we're going to take a melting point. We've already showcased that technique in a previous video, and I'll provide a snapshot of the temperature where it begins to melt and when melting is complete.